Good morning. This is Aerodynamics I. It is in incompressible flow over aerofoil. And this topic covers the following main important topics. It includes aerofoil nomenclature, aerofoil definition, and introduction on aerofoil characteristics, the NACA representation of aerofoil, low speed flow over aerofoil, that vortex sheet method, which is a numerical method, the Kuta conditions, the Kelvin circulation, again, the classical thin aerofoil theories of the symmetric aerofoil as well as the cambered aerofoil. And there's a definition of aerodynamic center, the lift flow over arbitrary bodies, which we have discussed in the previous chapter, that can be also summarized on the point of vortex panel method and the modern low speed aerofoil. So these are the topics to be covered. So in order to start this section, it is better to start from the historical perspective of aerofoil. As we know, from the Wright brothers now to yet, a lot of changes have been made on different aircraft design, so that is the part of the aerofoil. So aerofoil come in a different shape, and it can be of the cambered type, it can be of the symmetric type, it can be of laminar flow shape, super critical airflow sheet, and standard aerofoil sheet. So historic sequence of aerofoil shapes through from 1935, which is already given in this picture. For example, we can see from 1908, the Wright brothers designed an aerofoil, again blew it in 1909, and others also. Till 1935, we can find actually the NACA representation. Formerly, it is called NASA, which was provided with different 4-digit representation. The NACA 5-digit, NACA 6-digit are also there. So these are, some of them are supersonic aerofoil shapes. Others are supercritical aerofoil shapes, laminar flow aerofoil shapes of the 6-digit, so which are all given here. Actually, the source is from NASA. Okay, so the beginning from 1938, the National Advisory Committee for Aeronautics, which is NACA, developed a revolutionary series of aerofoil shape, which is designed to encounter laminar flow in the boundary layer. Again, beginning in 1965, again, the NASA, that is National Aeronautics and the Space Administration, developed another series of revolutionary aerofoil shapes, which are supercritical aerofoils, which are designated for efficient flight near Mach 1. Which is, and also typical supercritical aerofoil shape is already given in the previous, this is supercritical aerofoil. Okay. So the classic aerofoil shapes for supersonic flow, which are given here, this is the supersonic aerofoil, which is developed again. All these aerofoil shapes are already present in the first slide. So today, the proper design of new aerofoil shape is more paramount important. So using some numerical techniques, aircraft companies usually custom design the aerofoil shapes for new airplanes and shapes that best fit for the design requirement of the specific aircraft. So once we say this on the historical perspective of aerofoil, let's see what is the definition of aerofoil. So just it is a shape which is when we cut the aircraft wing at any specific location whatever we observe the shape from the front or from some what we observe is the aerofoil shape. So for example, this is half wing span. And if we cut this half wing span at some arbitrary location, and when we observe it, the cross-sectional cut portion of the wing, what we observe is the aerofoil shape. So that is, it is just a shape, okay? So let me provide a cross-sectional hatch for this wing cross-section actually. Okay. Okay, let me use. If we cut any section here, what we can observe is the shape, which is aerofoil, like this is the shape, aerofoil shape here. This is aerofoil shape. It is two-dimensional. In the three-dimensional wing, we can observe two-dimensional. And this aerofoil shape have different nomenclature. Actually, we can observe aerofoil, two-dimensional aerofoil here. This is a cambered aerofoil. So on that, we can observe different cross-sections. The length from the leading edge, actually the front extreme point is called the leading edge. The back edge is trailing edge. And the distance from leading edge to trailing edge is called chord. That is chord distance. And the line which joins the leading edge to the trailing edge, the straight line, is called chord line. Okay? And we have lower surface, we have upper surface. Again, the leading edge radius also is there. The radius which produces the leading edge. The location of maximum thickness, from the leading edge. We can check this as the location of maximum thickness from the leading edge. Again, maximum camber. This is a camber line. If you observe the curved line, which is dividing the aerofoil into two equal sections. Okay, the camber line is the line which divides a given aerofoil into the upper and lower equally. So at every point, if we draw a line from upper surface to lower surface, we can find T over 2 and T over 2, upper and lower. That is the camber line. So because this is a cambered aerofoil, it has a camber line, okay? And the camber is having a maximum camber at some point. So the location of maximum camber is somewhere in between there. We call that line as mean aerodynamic or mean camber line. So what is left now? Yeah, these are some of the technical words which we use when we are defining the aerofoil. So the straight line connecting the leading edge and the trailing edge of the aerofoil is called chord line, okay, which is represented with C. And the camber is the maximum distance between the mean camber line and the chord line, which is measured perpendicular to the chord line. So camber, the maximum camber which we call is this one. This distance is called maximum camber. And the location of maximum camber from the leading edge is this distance. Okay, this is the location of maximum camber. Okay. The thickness is the distance between the upper and the lower surface, also measured perpendicular to the chord line. Okay, so the thickness is this. This is a thickness. This is maximum thickness actually. Maximum camber does not guarantee the location of maximum thickness. Okay. So the shape of aerofoil at the leading edge is usually circular with leading edge radius of approximately 0.02 of the chord. Okay, so most of the representation in aerofoil is in terms of chord. Now let's see the NACA aerofoil designation. So NACA is National Advisory Committee for Aeronautics, which is the formerly the NASA family. So the shape of all standard NACA aerofoil are generated by specifying the shape of mean camber line and then warping the specific symmetrical thickness distribution and the mean camber line. So we have different NACA designation. One is 4-digit designation, 5-digit, 6-digit designation. Each of them have different meaning. So for example, the NACA 4-digit designation, NACA 2412 is 4-digit. So each of these digits are having meaning. Okay. For example, the first digit, okay, the second digit 4, and the last 2 digits are the representation. Here also we have 5-digit, NACA 5-digit. So each digit, maybe the last digit is still similar to that, maybe by not by the number, but representation is same. Again, the NACA 6-digit, 65, 3, 2, 1, 8. Okay, so this is the NACA 6-digit. Okay, so the NACA 6-digit maximize the regions over which the airflow remains laminar. So, and the representation, this is NACA 6-digit representation. So we'll see each of them. For example, NACA 4-digit 2412 represent the first digit 2 represent maximum camber as percentage of the chord. For the given chord, okay, the percentage of that chord gives us the thickness, maximum camber. It indicates the maximum camber. So as I told you, maximum camber is this thing. Okay, maximum camber. Okay, so the first digit indicates when we divide it by 100, it is indicating the maximum camber. The second digit, that is 4, indicates location of maximum camber. So the location of maximum camber means what? This is the location of maximum camber from the leading edge. Okay, so the location of maximum camber from here to here, and the maximum camber is this. So that is for the cambered aerofoil. This works for the cambered aerofoil. Okay, so yeah, and then the last 2-digit, that is 12, indicates maximum thickness as a percentage of the chord. Okay, 12% of the chord gives us the maximum thickness. Okay, 12% of, it is not 12% thickness, but it is just, I can correct it. This is 12% of chord C. Okay. So everything is represented with respect to chord. This is not actually camber, but chord. Okay, we designate everything. So once the chord dimension is known, then we can find the maximum camber, the location of maximum camber, and the thickness of aerofoil. Okay, so this is the NACA for digital representation. Look, so the NACA 4-digit 2412, MP and T. M indicates the maximum. Okay, so where is our M? 2 means 2% of location of the maximum camber. So the location of maximum camber is somewhere around here. It is 2% of the chord. Okay, then P is 4 in case that the maximum camber. Okay, M is equal to, it is not M, but yeah, here there is some kind of confusion that M indicates 2%, 2% of the chord. The location of maximum camber from the leading edge is 40% of chord. Okay, 40% for 40%. And the remaining 12 indicates 12% of the chord, indicates the maximum thickness. Okay, so where is the maximum thickness? Somewhere around maximum thickness is there. Yeah, maximum thickness, maximum camber, and the location of maximum camber. Okay. Location of maximum camber is the first representation. The maximum camber itself is there and the maximum thickness. NACA 4-digit, it is a common practice to state the number in percent of the chord, which is percent of 2% camber at 40% of chord with 12% of the chord is the thickness. So thickness is 12%. So an airfoil with no camber, which is known as symmetric airfoil, will have representation 0, 0, because we are not going to show the location of maximum camber and the maximum camber itself, so that they are represented with 0, 0. Okay, so 0, 0, 12. It has only thickness, so that we represent the symmetric airfoil. Symmetric airfoil indicates the upper and the lower surface are having in symmetry with the chord line. Okay, so that it is represented with 0. We have only thickness of 12% of the chord. Okay, maximum thickness is located somewhere, which is by represented with chord. The next 5-digit series, NACA 5-digit, 23012 or 23012 aerofoil, which is NACA 5-digit. So the first digit here indicates 3/2 of when we multiply it by 3/2 gives the design lift coefficient in tens. Okay. See, the design lift coefficient CLD is equals to 2 times 3/2 times 2 is the first digit here. Okay, times 3/2 is the multiplication for the design lift coefficient, and it is by tens, so that it is 1/10. Therefore, what we can get 0.3 is the maximum lift coefficient, design lift coefficient. The next 2 digits, when divided by 2, gives the location of. That means 3 and 0. We have 3 and 0 divided by 2 gives the location of maximum camber along the chord. Okay, from the leading edge. Okay, C maximum, which is 30/2 times C by the percent. So that percent represented by over 100. So 0.15 C. The final 2 digits gives the maximum thickness by hundreds. So 12 times C over, actually it is in not hundreds, it is, yeah, in hundreds. Therefore, it is 0.12 C. That is the maximum thickness. So for the NACA 5-digit aerofoil, the designation lift coefficient is 0.3. The location of maximum camber is 0.15. And the aerofoil has 12% maximum thickness. Okay. So this is just a NACA 5-digit series. So we have chord from here to here. Okay. Leading edge to trailing edge is chord. And we have maximum camber C max is given here. C max. Okay. that Cmax is actually we can find Cmax. Okay, using the first digit and multiply it by 3/2, what we can get is the design lift coefficient. And Cmax is 30/2, in case that. Okay, 0 means standard 5-digit aerofoil. 1 means maybe sometimes this 0 be represented either 0 or 1. 1 means reflexed camber, and 0 means standard 5-digit aerofoil. Okay, so the last 2 digits represent thickness. Okay, 100, that is thickness by 100. 6-digit representation, which is represented with 65 3 415 aerofoil. So this is a laminar flow aerofoil, which is developed during World War II. And the first digit simply defines the series of aerofoil. The second gives the location of maximum pressure in tens of cord from the leading edge. And the third digit is design lift coefficient in tens. And the last 2 digit gives maximum thickness in 100 of the cord. So for NACA 6 digit, the first 6 represents the series designation. This is the first 6 series. The maximum pressure occurs at 0.5 of the cord. That means the second digit. For the basic symmetric thickness distribution at 0 lift. Okay. And the design lift coefficient is 0.4. It is just the this digit. And the aerofoil is 15%. The last 1 and 5 is 50% of the thickness. So this is kind of 6-digit representation. Okay, the first 6 indicates series, and this next 5 indicates position of maximum camber, and these 3 indicates range of favorable lift coefficient, and the 4 is design lift coefficient, and the last 2 digits are the thickness of aerofoil. Okay, so this is the NACA 6-digit representation. We have also special purpose aerofoils, which are designed by different companies. For example, the major aircraft companies such as Boeing, Airbus, and others, they design custom aerofoils for their aircraft model. For example, Boeing 727, 737, 747, and so on, which they made custom design. Different aerofoils, like for example, Beechcraft, Sundowner, we have NACA 6-digit. Cessna 1.5, we have 4-digit. Gates or Lockheed Martin C5 Galaxy, for example, we have symmetric aerofoil NICA 0025. So these are just the designations. Okay, and design technique for modern aerofoil design use advanced computer actually to design. So among the techniques, the panel technique and the finite difference techniques are some of the techniques which we use for designing aerofoil. So when we go to the next topic, the aerofoil characteristics. Okay, whenever we are talking about different aerofoil, we are just talking about the aerofoil characteristics. Among them, so from 1930 to 1940, NACA carried out a number of measurements on the aerofoil of the lift, drag, moment coefficients on the standard NACA aerofoil, and also the pressure difference. So using low-speed wind tunnel. So wind tunnel is one of the instrument which we perform the experimental work of aerodynamics. So in this experiment, the flow sees a wing without wingtip, which is so-called infinite wing. So aerofoil is called an infinite wing. Why? Because which is theoretically stretched to infinite along the span in the y direction. Okay. So since the aerofoil section is the same at any span-wise location along the wing, the infinite wing, the property of the aerofoil and the infinite wing are identical. Therefore, aerofoil data are frequently called infinite wing data. And the actual 3D wing is called finite wing. So that the data which we obtain from the actual wing is finite data. Okay, finite wing data. So some of the characteristics which we define in case of aerofoil are the CL versus alpha graph represents the way how an aircraft behaves with angle of attack. Okay. So the variation of CL with alpha for aerofoil is already given here. So at low to moderate alpha, CL varies linearly with alpha. So as we see from some negative values to some value of alpha, the CL versus alpha graph is very linear, which indicates the flow is smooth flow with no turbulence. And the aerofoil flow pattern is given with smooth flow. So it is just characterized by an appropriate smooth flow, and the lift coefficient or the lift slope is given A naught, which is equal to change in CL over change in alpha. So DCL over D alpha is the aerofoil lift slope, which is linear, only which works on the linear region. But once it reaches to the maximum CL max, the behavior immediately change. So what happened? The flow pattern also on the aerofoil also is characterized differently than the previous. So the maximum point at which the CL becomes CL max is known as the critical angle of attack. The angle of attack which belongs to CL max is called critical angle of attack or stall angle of attack. And then once it reaches to the stall angle of attack, in the remaining section, the behavior of the curve is nonlinear and it is continuously decreasing. So that immediately encounters the aerofoil encounters the flow separation at the back of its shape. So the flow becomes having some turbulence and wake. Okay, that the turbulence and the wake on the flow region produces flow separation, and immediately the aircraft face stalling. Okay, stalling is a critical condition of the aircraft flight. Okay, so that is the characteristics. So in the region, the flow moves smoothly over the aerofoil and is attached over most of the surface, as we have seen there in the and as alpha becomes larger, the flow tends to separate from the top surface of the aerofoil, creating the large wake of relatively dead air behind the aerofoil. So inside this separated region, the flow is recirculating, and part of the flow is actually moving in the direction opposite to the free stream, so called a reverse flow. Okay. So the consequence of this separated flow at high angle of attack results the quick decrease in the lift and a large increase in drag. Under such conditions, the aerofoil is said to be stalled. Okay. So the maximum value of CL, which corresponds to the stall, is denoted by CL max. Okay, so and the stall speed is represented v stall, which is 2 times the weight of aircraft divided by air density times the span the aircraft's area, wing area times CL max. So this is the stall velocity. So the higher the CL max, the lower the stalling speed, as we can see. V stall and CL max are uh, inverse relation. That means under radical even. So at the other, actually the curve becomes nonlinear. CL reaches the maximum value and finally the airfoil stalls. At the other extreme of the curve, the lift at alpha is equal to 0, that is CL 0, is finite, which is induced the lift goes to 0 only when the aerofoil is pitched to some negative angle of attack. So actually, this diagram indicates CL versus alpha graph for cambered aerofoil. In actual case, for the symmetric aerofoil, the CL versus alpha graph passes through the zero line. Okay, 0, 0 coordinate. But here it is alpha is negative, but CL is 0 here. That is alpha L is equal to 0 is uh, the point where lift is 0 point. So for symmetric aerofoil, alpha at L is equal to 0 is 0, where as for aerofoil with positive camber, alpha L is equal to is negative value, usually on the order of -2 or maybe -3 degree, depending. Sorry. So experimental results from lift and moment coefficients for the NACA 2412 aerofoil are provided here. Actually, you can observe this. This is NACA 2412. So this is cambered aerofoil because 24 indicates the camberness. Okay, so it is not symmetric aerofoil and it has alpha value at 0 CL. Okay, so this is CL versus alpha graph and also CM versus alpha graph. Okay, and the second one is indicating the CD versus alpha. Okay, and also CMAC. CMAC is the moment coefficient at aerodynamic center, and CM C4 means C over 4 means the moment coefficient at quarter chord point. Okay, so that is a representation. So the force and moment system on aerofoil can be transformed commonly to the quarter chord point. That's why we use CM C over 4. That the experimental data are given for two different Reynolds numbers. The lift slope A naught, which is dCl over d alpha, is not influenced by Reynolds number. However, the CL max is dependent upon Reynolds number. So this makes sense because CL max is governed by various effects, and Reynolds number is similarly parameters that govern the strength of inertia force relative to viscous surface in the flow. So how we can define Reynolds number? That the Reynolds number is defined as RE. RE is equals to rho L V over mu. So rho is the air density that we can say rho infinity. L is the chord length actually for our aerofoil. V is the flow velocity, okay, divided by the dynamic viscosity mu. Okay, so that is the representation for Reynolds number. So these two graphs indicate the CL versus alpha and the CM versus alpha graph for quarter chord, the first, and the second indicates the drag and the moment coefficient. Okay, so the vertical axis indicates the drag, and the horizontal is the alpha. Okay, so and also the moment coefficient CM about aerodynamic center. Anyway, so based on what we have discussed yet, we can take some example. Just consider the NAC at 4-digit aerofoil with chord of 0.64 in the airstream standard at sea level. So, and the free stream velocity is given 70 meter per second, and the lift per unit span is 1,254 Newton per meter. Calculate the angle of attack and the drag polar unit span per unit span. So density is known for the standard sea level condition 1.23. The dynamic pressure Q is equal to half rho V square, so that we can calculate. Then we can calculate CL is equals to, actually that CL is directly from this formula. So lift per unit span L prime is equals to Q times the dynamic pressure Q times C times CL. So Q is already calculated, this one. L is already given, that is the given value. Chord is given, C is chord given, so that directly substituting this, we can find CL. So CL is 0.65. Okay, so we can go to the figure itself, the previous figure here. We can observe CL that belongs to 0.65. So where is the CL value 0.65? It is 0.8 is here, somewhere around. 0.68 is somewhere around here. Let me 0.6, 0.8, 0.4, so that 0.6 is here, somewhere at the middle, but 6.8 is around here. So tracing it here, straight towards to here, and bring it down like this in straight, then what we can get is the alpha value. That alpha is about 4. Yeah, if I appropriately sketch it, it is about around here. Okay, that I can trace it down like this. So it is 4. This point indicates alpha is 4. So the result, alpha is 4, is the alpha value that corresponds to 0.65 CL. So CL versus alpha graph can be obtained like that. Again, to obtain the drag polar per unit span, we must use the data in figure 4. Since CD is a function of Reynolds number, we can calculate a Reynolds number. So Reynolds number is equal to rho V C over mu. So mu is already known for such fluid. For air, at standard sea level, mu is equal to 1.789 times 10 raised to minus 5 kilogram per meter second. Therefore, Reynolds number is calculated from here. It gives 3.08 times 10 raised to 6. And using data for Reynolds number 3.1 times 10 raised to 6 in figure 11, we find CD. So the drag coefficient. So let's go to the okay. Actually, this representation of 3.1, yeah, Reynolds number 3.1 times 10 raised to 6 is this one. This diagram indicates Reynolds number, Reynolds number of 8.9 times 10 raised to 6. And this zero or the oval-shaped type of data represent for lower Reynolds number. So based on that, for alpha is equals to 4 degree. We can trace it from alpha is equal to 4 degree here. Okay. So alpha 4 is this one. I will go up like this point. And the point, and I will trace it back to CD like this. So when we are appropriately sketching it, we can get this result actually. So that is nearly 0.0068. 0068. Yeah, it is above 0.004, below 0.008. So that is 68. Yeah, we can approximate. Okay. Or we can perform some kind of interpolation in order to get exact. And then we can calculate drag. So drag is equal to Q times S CD. So CD is already obtained. Okay. S is given. Okay, 0.64. Actually, yeah. Q already calculated. Okay. And the unit area, what we have used is unit area. So S is taken 1. Okay. Simply taking S1, we have 13.1 Newton per meter. That is the drag force per unit length. So even we can now calculate the CL to CD ratio. Okay, we can calculate CL to CD ratios. That is one of important parameter. Okay, so that is the first question. We have the second question for an aerofoil and flow condition given in the previous exam. Calculate the moment per unit span about the aerodynamic center. So we have moment per unit span about aerodynamic center is given. Okay, this diagram indicates aerodynamic center condition. So it is simply moment about aerodynamic center, which is equal to Q times SCCM. Okay, C is the chord, CM is the moment about aerodynamic center, moment coefficient. So it is minus of 0.05. So we have some explanation that related with the previous topic. Actually, for today, I think that is sufficient. We'll continue from theoretical solution for low speed flow over aerofoil using vortex sheet method, that numerical method. Now, this is sufficient for today.